So this is going to be the last part on the chapter 5 on Cartan decompositions and maximal compact subgroups. And the last thing that we are going to do is to prove that the maximal compact subgroups of the automorphism group and the inner automorphism group of real semi-simple algebra are conjugate. So let's just recall the notation that we were using for this session. So for this part, so let G0 be a real semi-simple algebra. And we're going to define the terms that appear in the Cartan decomposition. So we fix our Cartan involution theta. Cartan involution theta, and the Cartan decomposition associated with theta, which is G0 equals K plus P. And then recall that we defined K to be the set of orthogonal elements in the automorphism group. It's essentially where the automorphisms that commute with the Cartan involution. Such that theta alpha is equal to alpha theta. We defined P to be the set of positive definite elements. And we already know by the Cartan decomposition theorem that this could also be recovered as the exponential image of at P. And recall that the connected component of K containing the identity could also be recovered by taking the intersection with K and the inner automorphism group. So recall that K is maximal compact in the automorphism group and K0 is maximal compact in the inner automorphism group. And we wanted to prove that these were unique up to conjugation by an element of the inner automorphism group in both cases. And the idea was to see that both groups fix a point by an adequate action on P. So we defined this action in the last section was the following. So we have essentially a change of basis action, an action of the automorphism group on P, which was essentially alpha dot P to be equal to alpha P alpha star. And both the automorphism groups and the inner automorphism group act transitively on P. So this turns P into a homogeneous space, and in fact it was a non-compact symmetric space. So we're going to find a fixed point for this action by exhibiting it as the minimum of an invariant function. And the idea is to see that this invariant function has a unique minimum, and this will be the fixed point. Okay, so I'm first going to make some general definitions that Onishik makes for Euclidean vector spaces, and the idea is to apply it to this G0. So let E be a Euclidean vector space with inner product, which I will be denoting by angles. Okay, so first recall that we call P of E the set of positive definite operators on E, which were also symmetric, and we're going to define a function by small r defined on PE cross PE, taking values on R, and it's going to essentially be the inner product of the first element with the inverse of the second element. So R is going to take theta and gamma to the trace of beta gamma minus 1. Okay, so obviously this is an analytic map because inversion is analytic, and to each compact subset of P of E, we're going to associate a function rho in the following way. So we have that R is analytic, and given any compact subset omega, so I'm going to contained in P of E, we also define a function rho omega defined on P of E and also taking values on R, that given any element beta is going to take it to the maximum over the elements of omega of R of beta gamma. So the maximum gamma is in omega of R beta gamma. So obviously this is a well-defined map because we are assuming that omega is compact. So we're going to be working with these two functions. It's more or less easy to prove that this map is continuous, and I'm going to leave it as an exercise. So I'll just write it here. So what I'm leaving up to you is to prove that rho omega is continuous for every omega. So for example, one way that I think is very simple to see in this setting is to prove it by sequences. So for example, you can take a sequence beta I in P of E and use a very simple compactness argument in order to see that rho omega of beta I converges to rho omega of the limit of beta I. Okay. So the first thing that we're going to do is to try to give a more useful description of this function rho omega, and we will see that it's coercive and in a sense it's convex on one parameter subgroups. So first, note that the elements in P of E can always be diagonalized, and this is going to be helpful in order to try to describe these maps R and rho omega. So I now give a more explicit description of the map. So for the moment, let's fix an element beta. And we can always find an orthonormal basis of eigenvectors for beta because beta is a positive definite symmetric linear map. So we may choose an orthonormal basis. So let's call it E1 up to E1 up to the n that consists of eigenvectors. And say that the eigenvalues are lambda I. So what we would have is that beta of d sub I is equal to lambda I d sub I, where the lambda I are positive constants. Okay, so if we try to describe R of beta gamma, we could write any gamma. Well, the inverse of gamma can be described in the following way. So the inverse gamma if we write it in terms of the coefficients, it can be written in the form Gij, where I and j range from 1 to n. And then we will simply have to take the trace of a diagonal matrix with an arbitrary matrix. We obtain the following, that R of beta gamma is the trace of a certain diagonal matrix, lambda 1 up to lambda r, times a square matrix. And it's very easy to see that this is essentially the sum of the products of the diagonal elements. So this is simply sum from I equals 1 to n of lambda I to gi. So note that since we are considering orthonormal bases, these matrix coefficients of gamma minus 1 can be recovered as scalar products, and the ones that we are going to be interested in are precisely the diagonal ones. So I'm just simply going to recall that we can recover Gii as the inner product of Vi with gamma minus 1 of Vi. Okay, this is going to take an important role in the first lemma that we are going to prove. Okay. So, and lastly, before starting with all the lemmas that we're going to need in these two functions, I will recall the definition of the norm induced, the matrix norm induced by the Euclidean norm. So given, so we denote by beta the norm of beta induced by the norm of E. So this is simply the maximum where V is in E.
Sorry.
Yes.
Would it be okay if you turn your tablet the other way around, because it's a little bit difficult to copy?
Okay. Okay, so we were defining the operator norm of beta induced by the norm of E, and this is simply the quotient of the of the norm of beta V with the by the norm of V. So this is for non-zero elements of E. Okay, and it's a well-known fact that in the case that we're considering symmetric or positive definite, in the case of positive definite symmetric operators, this norm coincides with the maximum eigenvalue of beta. So if beta is positive definite, then the norm of beta is the maximum eigenvalue of beta. Okay. So now we start with the series of lemmas that will be needed in order to prove the conjugacy theorem. So firstly, we will see that this map, the rho omega, is always a coercive map. So lemma, if you take any omega that is compact, then there exists a positive constant that only depends on omega, such that rho omega of beta is always greater than or equal this constant times the norm of beta for all positive definite beta. And the proof is very simple because we already have above the expression of R of beta gamma. So essentially, it's a linear combination that involves the eigenvalues of beta and the inner products of unit vectors with the image by these gamma minus ones of unit vectors. So since the sphere is a compact subset, the idea is that we can also always find minimum values for these G sub I, and then we can bound this by below by a constant times the trace of beta. So, okay, so I'll just write it down for the proof. Essentially, note that if we consider a function of the form that takes omega and b, and where omega is in, so gamma b, where gamma is in omega and b is in the unit sphere E, and takes it to the inner product gamma minus 1b, to the inner product of gamma minus 1b with v. This is precisely, so this is a continuous function defined on a compact topological space, so it must achieve a minimum. And all of these elements gii lie in the image of this function, so they are always bounded below. So write it down. So this is continuous on a compact space. So there exists a positive b such that gamma minus 1 of b, inner product b, is greater than or equal to this lowercase b for all b and gamma. Okay. So in the above expression, we get that R of beta gamma is equal to the sum of this lambda i's gii, and this is greater than or equal b times the sum of the lambda I, and obviously the sum is greater than the biggest eigenvalue, so this is greater than or equal to b times the norm of beta. And now remember that the function rho omega is defined as the maximum of these R beta gamma. So obviously it's also greater than or equal to b times the norm of beta. Okay, so essentially we have this continuous and coercive map, and it will follow essentially that it always attains a minimum in every closed subset. Essentially, the way to see this is via compactness argument, which we will describe now. So this is in the form of this second lemma that states the following. So if F is a subset of P of E that is closed in the set of symmetric elements, then the function rho omega always attains a minimum on F. On F. So proof. Obviously, this is true for compact subsets, and the idea is to reduce these the setting of the lemma to the case of an adequate compact subset. And the easiest way to do this is to consider the elements that have whose image is bounded by above by, for example, the image of a fixed element. So fix an element beta 0 and let P be the set of elements in F whose image by rho omega is smaller than the image of beta 0. Okay. So obviously this is a closed subset of the symmetric elements of E. So P is closed. And we have to see, to check that it's compact, that it's also a bounded subset. And this is essentially because of the previous lemma. So it's bounded since if you take any element beta in F, we know that the norm of beta is bounded by above now by 1 over b, where b is the constant in the previous lemma, times rho omega of beta. And since we are in F, this is obviously less than 1 over b of rho omega of beta 0. So hence, this is a compact set. This is compact. And we know that rho omega must have a minimum in B. And obviously, since the elements outside of B have image larger than rho omega of beta 0, and this element is already larger than the minimum, this minimum is also a global minimum. So this is essentially the first property that we need of the function, and it's that it achieves a minimum in closed subsets. So for now, everything more or less understandable? Is it clear for now?
Yeah, it's good.
Yeah, sure.
Okay. And the second property that we need now is to see that this mapping is convex in the direction of one parameter subgroups. Okay. So for this, we will need a small lemma that can relate the convexity of R with the convexity of rho omega. So I'm not going to write the definition of convexity, but it's but we all know what it means. It's essentially that the image of if you have any 2 points, and you draw the line between the points in the graph generated by those 2 initial points, then the graph is always below that segment. Okay, so have the following lemma. So suppose that we have a topological space omega that is compact. And suppose that f is a function defined on r times omega with values on r, and is continuous. So from this function, we're going to define a new function taking the maximum in the second variable. So let f of t be equal to the maximum of f ts, where s is in omega. So this is a real function of a real variable. And the lemma states that if whenever we fix a point in omega, the function that comes from fixing this second variable is a strictly convex function, then this lowercase function, this lowercase f, is also a strictly convex function. I have to remember that it's strictly convex. Then f is also strictly convex. Okay. So what we need to check is the inequality corresponding to the property of being convex. So we need to check that if we have a certain interval AB and an element T that is strictly in between A and B, the image of T under F is strictly less than f of A times B minus T over B minus A plus f of B times T minus A over B minus A. Okay. The idea is the following. Essentially, since we're taking the maximum, we can always write f of t as capital F of a t comma s of t, where s of t is an adequate choice of s. So for any t, we simply choose an s of t in omega such that f of t is equal to capital F of t comma st. We do not need this choice to be continuous or anything like that. The only thing that we know is that we need is to know that it exists because omega is compact. Okay, so now we simply write f of t. Then by definition, it's capital F of t comma s of t. And by our hypothesis, this function is convex in the first variable. So this must be less than f of a comma s of t times b minus t over b minus a plus f of b comma s of t times t minus a over b minus a. Okay. And now obviously f is taken to be the maximum, so this first value here and this second value here are both bounded by lowercase f of a and lowercase f of b. So this is less than or equal to f of a times b minus t over b minus a plus f of b times t minus a over b minus a. So this function is a strictly convex function. And now we simply apply it to the functions r and rho omega along one parameter subgroups. Okay, so lemma fix beta to be positive definite and a compact subset omega. Then the function f of t equal to rho omega of beta to the power of t for every real t is strictly convex. So in particular, we can, if this function has a minimum, then this minimum is unique by a standard convexity argument. So for the proof, to note that we're essentially in the setting of the previous lemma, because rho omega of beta of t is the maximum over elements of omega of r of beta to the t, comma, gamma. Okay, so in reality, by the previous lemma, we only need to check that this last function, r of beta to the t, comma, gamma, is a strictly convex function of t. And this is going to be pretty much obvious from the previous expression that we have for r. So from the expression r in terms of the an orthonormal basis, we have that r of beta to the t, comma, gamma is equal to the sum over I of Gii, where the Gij denoted the matrix coefficients of gamma to the -1, times the eigenvalues of beta to the t, because beta to the t has the same eigenvectors as beta. And the eigenvalues of beta to the t are precisely the eigenvalues of beta to the tth power. And this can be written equivalently as the sum over I of Gii times the exponential of t times the logarithm of lambda I. Okay? So remember that these constants Gii are always positive because we're in the positive definite setting. So we may apply, for example, the criterion for the second derivative, and we see that this is strictly positive, so this must be a strictly convex function. So this is a strictly convex function. Okay, and now by the previous lemma, we simply obtain that rho omega is strictly convex along this curve. this is strictly complex. Okay. So yeah, this is pretty much everything that we need in order to prove this the last conjugacy theorem. So far so good.
Yeah, it's perfect.
Okay, right. So now let's prove the main theorem. So just write the statement again for the sake of completeness. So I wanted to prove the following. So let L be a compact subgroup of either the automorphism group or the inner automorphism group. Or inner automorphism group. Then there exists an element Q in P such that if you conjugate L by Q, then this lies inside of K. Okay. Thus, maximal compact subgroups are conjugate. Inner automorphism group are always conjugate. Okay. So let's go with the last proof. So we're going to set the Euclidean vector space to be the Lie algebra G0 with the scalar product induced by the Cartan evolution. So set E to be equal to G0, the scalar product P theta. Okay. So first, we know that this function rho omega attains its minimum in closed subsets. So first, we're interested in seeing that the set P is closed in the set of symmetric elements of G0. So first, P is closed in S of G0. Okay. And this is because of the following chain of inclusions. So first, P is inside of the inner automorphism group of G0. This is part of the Cartan decomposition theorem. And it's also closed, again, because of the Cartan decomposition. It's a factor of the inner automorphism group of G0. Now, the inner automorphism group of G0, since we're always in the semi-simple case, is the identity component. And so it's a closed subset of the automorphism group of G0. And the automorphism group of G0 is closed in the set of all operators in G0. So this chain of inclusions, so everything is closed in the next factor. Okay. So this is a chain, closed inclusions. And well, since P is closed in GL of G0, it must also be closed in S of G0. P is closed in S of G0. So now in this context, we can consider the previously defined functions R, now restricted to P, and the row omega from P to R, where we consider omega to be a compact subset of P. Okay. So now, by the, I think it was the third lemma.
Can I ask a question?
Yeah.
Why is the last inclusion a closed one? Like the automorphism group should be closed in the set of invertible operators because it's just like a stabilizer of the Lie bracket. But why is it closed in the set of all operators?
In the set of all operators.
Why can't you have like a sequence of automorphisms which converges to something that also preserves the bracket but is degenerate?
Okay. So maybe see if I can put a note here because I think you're right. Maybe I missed something here. The automorphism group in G0. So obviously it's closed in the set of invertible linear automorphisms. Yeah. And in the general case, can you have something that?
Well, yeah, maybe like the semi-simple case is special, but if your Lie algebra is abelian, then this is just the whole big GL which is open. So unless there's something special coming from the semi-simple condition, I don't see why it should be closed.
You got me here. I mean, it's been so long since I wrote this here. Check for a moment what Onishik had to say about this, because I think Onishik didn't give too many details on why P is closed.
Yeah.
Maybe this was a mistake on my part. Let's see. Int G0 is closed. Okay, so Onishik says. So let me reproduce Onishik's proof here. Maybe, yes, so scratch this. Okay. So obviously we have that P is closed in the inner automorphism group of G0. Again, this is because of the Cartan decomposition theorem. This, I think this doesn't have any problem. Now, since G0 is semi-simple, the adjoint image of G0 is inside of SL of G0. Okay. And now, he says, using this inclusion, one deduces that the inclusion of the inner automorphism group is closed in GL of G0. And he doesn't give any details. So he explicitly says, using this inclusion, one deduces that the inner automorphism group, which is contained in SL of G0, must be closed in the Lie algebra GL G0. So why would this be the case? Because probably I thought about this when I wrote the notes, but
what's the simplest example? Like if you take SL to C, then it's
so you have SLG0. So first, why should this be a closed inclusion? This inclusion, not the inclusion in GLG0. Why should this be closed?
Well, this is because like all automorphisms are closed in GLG, in big GL, in the Lie group.
Okay, but now SLG0 is closed in GLG0.
Yeah.
Because it's determined, it's the condition
Yeah,
determinant
yeah.
equals 1.
Yeah.
So
that's clear. But this one's.
but now it's all clear, right? So P is closed in the inner automorphism group. The inner automorphism group is closed in the automorphism group.
Oh yeah, because the determinants can
sequentially go to 0 because
Yes.
they're always 1. Yeah.
Yeah.
That makes sense.
Okay, so yeah, now everything is a chain of closed inclusions.
Yeah.
Okay, so that's how it works. So thanks for pointing it out because I totally missed
Thank
it.
you.
So this is a chain. Okay. So since P is closed, we can now consider the functions R and rho omega, where we consider omega to be a compact subset of P. So now we know that this function rho omega attains a minimum in P. So we know that rho omega attains a minimum at, say, beta 0. Certain beta 0 in P. Okay. So now we will need to use the convexity and the invariance now in order to see that this beta 0 must be unique. So first, let's try to describe the behavior of R and rho omega under the action of the automorphism groups. So note that if you take any automorphism, so what we have is that R of the action of alpha on beta and the action of alpha on gamma, then this is the trace by definition of alpha dot beta times alpha dot gamma minus 1. And this is the trace of alpha beta alpha star and the inverse of alpha gamma alpha star. And this is equal to the trace of, note that this alpha star here cancels out with the last alpha star. So this is alpha beta gamma minus 1 alpha minus 1. Now, since the trace of xy is also a trace of yx, we can cancel out this alpha and this alpha minus 1. So this is the trace of beta gamma minus 1, and this is equal to rho of beta gamma. So what this is saying is that R is invariant under automorphisms. This doesn't necessarily mean that rho omega is invariant under automorphisms unless omega is also invariant under automorphisms, but we can make a more precise statement about this. So to be a little bit more general, we have that rho omega of alpha dot beta, this is the maximum where gamma runs through all of omega of R of alpha dot beta gamma, and this is equivalent because R is invariant to the maximum over omega of the function R beta comma, alpha minus 1 dot gamma. So this is essentially rho of alpha minus 1 omega acting on beta. So in particular, if omega is invariant under the automorphism alpha, then rho omega is also invariant under alpha. Okay. So we now prove that this beta 0 point, this point of minimum is unique. Proof. The 0 is unique. So without loss of generality, since both the automorphism group and the inner automorphism group act transitively, we can consider beta 0 to be equal to E by using an adequate translation. So we may assume that beta 0 is the identity. And now suppose that we have another minimum point. So suppose that beta is another where rho omega attains a minimum. And then we can connect beta 0 and beta with a one parameter subgroup, which is essentially beta to the t. So we can consider the function rho omega evaluated at this parameter subgroup, this one parameter subgroup, and this is a convex function. Strictly convex function. That attains at minimum at t equals 0 and t equals 1. The global minimum t equals 0 and equals 1, and this is a contradiction. So this shows that given any omega, the function rho omega will only have one minimum point. So please. Point. And now just to finish, we simply have to make an adequate choice of omega to make this function rho omega invariant. And this choice is to simply take the orbit of the compact subgroup that we are taking into consideration, which I think we called L, the L given here. So to finish, simply let omega to be the orbit of L, which is invariant, and let beta 0 be the only point where we have a minimum. Point. Okay. So essentially now we are done because rho omega is invariant and beta 0 is the unique point where it attains a max, where rho omega attains a maximum, so it must be fixed under the action of beta 0. So L dot beta 0 is equal to beta 0, and this is the same as saying that L is contained in the isotropy subgroup of beta 0. Okay. Thus, so recall that in terms of the action, we could write beta 0 as Q times E, where Q is beta 0 to the 1/2. Okay. So what we have is that L is contained in the isotropy subgroup. So say, for example, in the case of the automorphism group, the isotropy subgroup corresponding to Q of E, and this is the same as Q times the isotropy group at E, which is K, Q minus 1. And obviously Q is an element in P. Okay. Because the one parameter subgroup of beta 0 is totally contained in P. Okay. And now this proves the conjugacy in the case of the automorphism group. In the case of that we're considering only the inner automorphism group, so everything still works. And the only difference is that now the isotropy subgroup, so it's essentially the isotropy intersection, the connected component of the identity. So essentially, in the case of this inner automorphism group, we have that L is contained in the isotropy subgroup of Q times E, and this is Q, the isotropy at E, Q minus 1. And now this is Q, the intersection of K with the inner automorphism group, Q minus 1. And now this intersection, because of the Cartan decomposition, we already saw that is precisely K0. And now this finishes the conjugacy theorem. So we only proved this for the automorphism and inner automorphism group of a real semi-simple Lie algebra, but it's a very well-known fact that in reality, if you have a connected Lie group, then it always has the maximal compact subgroups are always conjugate. In the semi-simple case, the proof is not too different, and one can also argue geometrically by using the Cartan fixed point theorem, like we commented on the previous session. But yeah. And now, just to finish, I'm going to briefly discuss this last example that Onistic gives us for the realification of a complex semi-simple Lie algebra, and who exactly are the maximal compact subgroups associated with this complex semi-simple Lie algebra. So, final example. Suppose that we have a complex semi-simple Lie algebra G. Then remember that we already saw the Cartan decomposition associated to the realification of G, which was that the realification of G could be seen as U times U plus I times U. where U is any compact real form of G. Okay. And now if we take G to be equal, for example, to the inner automorphism group of this realification, which is essentially the same as the inner automorphism group of G, regarded as a complex semi-simple Lie algebra because it's generated by the exponential of the elements of the form at x. So essentially by the conjugacy theorem, there is only one maximal compact subgroup, and it's given in the following way. If you take the connected subgroup with the algebra at K as in the Cartan decomposition, so in our case is at U, this is essentially isomorphic to U, then this is a maximal compact subgroup. So what we are saying is that these maximal compact subgroups of the Lie group G are in a one-to-one correspondence with the possible conjugates of U, but these are precisely all the possible compact real forms of G. So therefore, we essentially have that maximal compact subgroups of G correspond to compact real forms of the complex semi-simple algebra. Okay. So this is essentially everything that I wanted to discuss for this chapter. So just as a side note, I will upload to the webpage the notes corresponding to this chapter, and I also added at the end a small appendix in case that anyone is interested, which is an extension of the Cartan decomposition theorem for an arbitrary semi-simple Lie group, and it essentially follows the approach in the book by Hilgard and Nip, and it's basically to replicate what we have done for the automorphism group and recover everything to the general case by simply noticing that the adjoint representation is a covering. One can find it's a pretty standard result. So this is essentially what I took from Hilgard and Nip, and one can also find it, for example, in Knapp's book or pretty much any book that includes theory of semi-simple Lie groups. But yeah, I think this is everything for today.